Good morning, Titans. It's Mr. Craig. Taking a look at kinematics, very first look actually, for some of you, it would be for Physics 11, similar in Physics 12, except we do 2 dimensions instead of just 1 dimension. So in grade 11, we look at motion in 1 dimension, which is just forward, backward. But in grade 12, we look at it in 2 dimensions, which would be like north, south, east, and west. As you can see, kinematics is just the 2 words put together, like kinetic and matics. Kinetic meaning motion, and matics meaning study. So it's really the study of motion. And really in terms of variables, things that you've encountered in your life, things that we can actually represent in math, it's all about distance or displacement, velocity or speed, A for acceleration, and T for time. Variables of kinematics are displacement, velocity, acceleration, and time. Displacement, sometimes called distance. There is a difference between them, but I don't want to go into it now. Velocity is sometimes called speed. Velocity really depends on speed and direction too. But again, I don't want to get into that right now. Acceleration and time. The units for these things in physics are for displacement. It's in meters. And those are m's. Velocity or speed is in meters per second. Acceleration is in meters per second squared, and I'll explain more about that later too. And time is in seconds. And we've got an abbreviation for seconds as S's. I think you've got a pretty good idea of what distance is, velocity even, speed. But what is acceleration? A lot of people think of acceleration as speeding up, but it could be slowing down. Speeding up would be a positive acceleration. Slowing down would be a negative acceleration. Really what an acceleration is, though, is a change in velocity. So it could be a change in the direction of the motion of the object, or it could be a change in the speed of the object. So really, acceleration is some sort of change in the velocity, but in a certain amount of time. So in a period of time, right? Change in time. So we write it down as acceleration. A is equal to change in velocity over change in time. So some sort of time interval over which the velocity changes. That is the acceleration. Has weird units. It's a change in velocity, which is like meters per second in a certain amount of time, like in a certain amount of seconds. So it's really meters per second change per second. So we say that it's a meter per second change per second. So these units would look like meters per second per second. And if you do the math on that, that just turns out to be meters per second squared. So it's got an odd unit, meters per second squared, but whenever you see that unit, you know it means acceleration. Yeah, so this unit, meters per second squared, really does mean something. Like, to give you an example, we've got a constant acceleration on Earth due to gravity, and that gravity acceleration is a different color. So the acceleration due to gravity on Earth is equal to about roughly 10 meters per second squared. And what that really means is if you fall for 1 second, then your speed increases 10 meters per second. So your speed at the end of 1 second is 10 meters per second. If you fall for 2 seconds, your speed is 10 meters per second plus another 10 meters per second, because it increased 10 meters per second for each second that it fell. So it'd be 20 meters per second. After 3 seconds, it would be 20 plus another 10, which is 30 meters per second. If it was after 5 seconds, then it would be 5 times 10. So it would be 50 meters per second, because it fell for 5 seconds. If it was on Jupiter, though, and I'll do Jupiter in green, they have an acceleration of roughly 25 meters per second squared. So if it was on Jupiter, after 1 second, it would be going 25 meters per second. After 2 seconds, it'd be going 25 plus another 25. So it'd be 2 times 25. And after 3 seconds, it would be going 75 meters per second, and so on, increasing 25 meters per second for each second that it fell. What you right now is just a picture from an old textbook, the Heath textbook, Fundamentals of Physics, that shows a couple of balls, this case a softball and this one a baseball, and they're falling due to gravity. So the acceleration due to gravity, which is about 10 meters per second squared, is causing both of them to fall. Notice that whether it's the softball or the baseball, doesn't matter, because gravity doesn't care what object it is. It could be me too. It would pull me down at the same rate, about 10 meters per second increase per second, and it's doing that with the softball and the baseball. Notice that they spread out, the distance increases quite a bit for each second that it falls, but it increases more the longer it falls. That's no surprise, because it is accelerating, it's speeding up. If we look at the balls that fall under the influence of gravity, they have a distance versus time graph that always looks like this. After 1 second, it'd be about here. After 2, it'd be about here. 3, it'd be about here. 4, it'd be about here. And if we had 5 seconds, it would be about right around here. So we end up getting a graph that shows this speeding up, that it's going a greater distance per second for every second that it falls because of its acceleration. So if we were to actually draw this graph, it looks kind of like this. Not a straight line. In fact, if you were to do the mirror image and pull this side out this way, it's a half parabola. And a half parabola is a parabola. It has an equation that's something like y equals x squared. So don't be surprised that one of the formulas for kinematics is something like a y equals x squared type of graph, type of equation. So using that graph that we drew earlier, the d versus t graph, it is a parabola, and d would be like the y, t would be like the x. So it's going to be something like d is equal to something t squared. In fact, when you do the math on it, based on observations that people take out in the field, and we will do in physics class too, you end up getting an equation that's d is equal to t squared. There's a few constants in here though too. So it's 1/2 times a in front of t squared, and there is like another variable here, VIT. It's like another constant. It would almost be like a y-intercept if you were looking in a straight line. But that's one of the equations of kinematics. If we look at the data of a falling ball or a falling human or a falling car even, we'll get a straight line graph of velocity versus time. if it's under the influence of gravity or some other constant acceleration. It's a straight line. So you're going to have an equation that looks like a straight line, y equals mx plus b. So that straight line equation is actually v is equal to some sort of constant, which in this case is the acceleration, times t. But there's a little more to it. Just to expand this equation to look like the one that we see in the textbook, it's just v final equals v initial plus at. So there's the slope, the a, and there's the variable t. If you combine equation number 1 and number 2, you end up getting an equation that looks like this. So Vf squared, final velocity squared, equals the initial velocity squared plus 2 times acceleration times the displacement or distance, depending on sign. Okay, so Vf squared equals Vf squared plus 2ad. The other equation is d is equal to Vi plus Vf over 2. That's just the average velocity times time. So those are the 4 equations of kinematics. And just to clarify, d is displacement in meters, a is acceleration in meters per second squared, Vf is final velocity in meters per second, and Vi is initial velocity, also in meters per second.